This is a demonstration of the OMFIT NIMROD module. So I'll start by importing the NIMROD module. And if you are a person who already knows how to use NIMROD and you just have never run NIMROD using OMFIT, you're the target audience for this video. Although if you're just getting started with NIMROD, that's great too. But perhaps the demo video will persuade you that there is some value add to using OMFIT with NIMROD, and it's not just adding an extra layer of complication. Okay, so I've loaded the NIMROD module into my OMFIT project. Actually, the very first thing I'm going to do is save my project because it's good to have a project name when you're using the NIMROD module. So I'm going to call this NIMROD demo, and then I will just save it right away. Okay, so we'll go through what these things underneath the NIMROD module are, but first I'm just going to double click here on NIMROD, and it's going to bring me to the setup GUI. So the setup GUI is what I use to set up my first simulation. So I can rename this if I want, whatever I want to call this first simulation. And so there's different ways you can set up a run. I'm going to do it the simplest way, which is I'm just going to start by finding a nimrod.in file that I have, and I'm going to load that into the GUI. So I'm going to click here. And so I'm going to find my file. All right, so here's the nimrod.in file that I want to start with. Now it's read my nimrod.in file and realized that I need a flux grid file. So I'm going to look for that, and that'll be in the same directory. And then it's read that and decided that I need an EFIT file, so I'm going to look for that. And that's all the files that I need for this simulation. So I'm just going to click Setup Nimrod. And now my GUI is going to change. I'm going to close it and open it again. It should resize automatically. The fact that it didn't is peculiar to running OMFIT on my Windows laptop. So now I'm in the main NIMROD GUI. So these are some of the inputs, of course, here in the GUI, not all of them. Some of these are ones you may want to change frequently, but to access all of the inputs that you have in your files and change them, you can click on the nimrod.in GUI. You can click on the fluxgrid.in GUI. So change any of those parameters that you want. I'm just going to change one thing. I'm going to make this case a lot more resistive because I'm going to run it for a very short time for this demo. It's also a pretty low resolution case for the purpose of the demonstration. So now I'm going to go to the Run tab. And I'm going to run my simulations on Cori at NERSC. As I said, I'm running OMFIT on my laptop. And this is just asking me what preprocessor I want to run. Usually I always use FGNIMIQ, but because it's very quick, I'm going to use nimset for this demonstration. And then I need to tell it where my installation of NIMROD is on the server that I'm going to be running. So I could just type that in, but I'll do this and I'll look for it on Cori. So I'm going to go to my installation. All right, so this is the directory where I have NIMROD installed. All right, so now down here where it says run job, I'm going to change this to run preprocessor only. So you probably want to run your preprocessor first, make sure your grid looks okay, everything looks okay. So that's what I'm going to do. And I'm just going to go ahead and click run nimset. So it's going to upload my input files to a directory on Cori. It's going to run nimset, and it's going to download my output file. So here under runs, I have this first simulation that I set up, and I have my inputs and my outputs. These are the input files that I loaded. An equidisc file always has an automatic plot associated with it in OMFIT, so I can actually click on that and see a plot of my G file. This is already finished. It's run nimset. It's downloaded the outputs, so I can go to outputs and outputs nimset. And so here are all the output files. It will parse many of these files, so you can make plots of individual data. The grid file has an automatic plot associated with it, so I can double click on that and plot my NIMROD grid. There are some files here that aren't parsed and or don't have automatic plots associated with them. Anything you want to plot that it's not straightforward to plot through OMFIT, you could also always fall back on using xdraw. I don't use it much, but you have that option. You can you have to set it up just once, and you do that by first telling it where to find your xdraw executable. So I'll tell it where to find that on my laptop here. And then also tell it where to find my draw files. So this directory contains all my draw.in files. So once I've set that up, if I want to plot something with xdraw, I can just do, say draw pack.in, and I'll plot my pack.bin file, make xdraw plot, and it will just launch xdraw for me. All right, so I'm going to go back over here to my run. So suppose I've checked everything out and everything looks good to me, and I want to run Nimrod. So I'm going to run it with a batch script. So I'll select run with batch script. I'm also going to click restart. I don't want to rerun the processor, so I just want to start from the dump file that I already have. So now when I say with batch script, this batch job tab appears, and I have to set that up. So I want to run this on 8 processors because I have 4 grid blocks and 2 layers. 8 processes per node. I'll put in the name of my repo. I want this to run quick for the demo, so I'm just going to change this, debug, and I'm going to change the runtime. I don't even need 10 minutes. So I can click generate batch script, and I'll get a batch script in my tree. I don't have to click that. It will generate it automatically when I click submit Nimrod job. So that's what I'm going to do. I'm going to click that, and it's going to upload my input files, my batch script. It's going to submit the batch job, and then it's just going to return, because it's not going to sit there and wait for the job to run. Of course, it could be in the queue for hours, days, weeks. But at some point, if I'm wondering if my job has started running, I can click this button that says check job status. So it's recorded the batch ID, and it's checking where it is in the queue now. So you can see it's running for 12 seconds. And I happen to know that this particular short job that I am using for the demo will be done running in a matter of another few seconds. If at some point I click the check job status button and it says no job, that means that it's not in the queue anymore, which should mean that it's finished running. And when my job is finished running, I can click fetch results, and that will get all of the results of the Nimrod run into my tree, except the dump files. By default, the dump files stay in the run directory on the server, and there's a way to automatically archive those later, but they're not pulled down into your tree by default. So this is fetching all of my outputs. And you can click that button while the job is running as many times as you want. You want to see how your job is doing when it's only been running for an hour out of 24 hours. You can click that button as much as you want. This button just opens your nimrod.out file if you just want to look at that. But then what we can do, we have under outputs Nimrod here now we have some files, and we can go to the plots tab. So again, if you like using xdraw, you can do that, but there's a button down here just for plotting your energy.bin files. So I'll close that one, but here's magnetic kinetic energy for the two modes in my simulation. This one plots your discharge file. So here's a bunch of different plots from the discharge file. Here's a kind of simpler one that's just total energy, thermal energy, plasma current. So, and then we want to run our post processors. So before I do that, actually, I'm going to come back here and I'm going to submit a second job. I'm going to show you how to do that. And then we'll run the post processor. So if I want to do another job, I just give it a new name. I click go. And then I can set it up to start with all the same inputs from the first run. So then I just do that. And now let's say I want to change just one parameter. I want to increase K-perp by a lot. So this is basically going to cause a thermal quench here. And so everything else I want it to be the same. I'm going to unclick restart. So now when I click submit NIMROD job for this new one, it's just going to run nimset automatically and then start the NIMROD job. So I'll just let that run and wait for it to submit NIMROD. And then I'll show you how to do post-processing on that first job. Okay, so that job has been submitted. And so now if we go over to post processor, what we want to do is go back to the first job. So you can always switch back and forth between which job you're working on just with this pull down up here. So I'm working on my first job that I've already run, and I want to run the post processor. So this is the GUI for using nimplot. So I have all the normal options. I'm going to make a contour plot. I want to tell it which dump files to use. I can just say something like range. So those are the dump files I want. And then I'll leave all these other settings the way they are. These are just all the inputs for nimplot, and I will put a string here that will make the name of my contour file unique in the tree, and I will click run nimplot. All right, so it finished. It got the contour file in my tree under outputs nimplot. And I'll show you, it also has a log file that gives you all the input parameters that you use to make that contour file. And the contour file is parsed, so you can write a script that refers to any particular variable in it. I'll show you how to make simple plots with that. But first, let me actually submit a job to run nimfl. So the nimfl GUI has all the inputs here for nimfl. I'll just leave these the way they are. If you want to run the parallel version, you just leave that checked. And you can load in a batch script if you want, but you don't need to. It will auto-generate a batch script for you, which is specific for running nimfl. That's also true if you run the parallel version of fgnimEq, which I skipped over by running nimset, but it should auto-generate a batch script for you. So I'm going to click run nimfl. And while that's running, I'm actually going to go over to the plots tab. So I want to plot the contour file that I generated, and that's this one. So I'll select that. And then it says, what am I plotting? Maybe I want to plot the toroidal current density, and I have many slices in my file. I can pick all of them or one particular one. And then it gives me some other options here. I can overlay poloidal flux. That's going to calculate poloidal flux on the fly using the B fields that are in the contour file. So I'll click plot. There's a plot of my toroidal current density with poloidal flux contours. Or I could plot the temperature. I want to plot all of them, and I want to overlay Q, so it'll make contours of Q on all of my plots. And so here is Q equals 1.5, Q equals 2, etc. for all of these time slices. So nimfl finished running, and as soon as the job is out of the queue, it will download the results of that. So that's happening right now. All right, so my nimfl file is in my tree now, so I have outputs nimfl. You can actually just click on it and it'll just give you a plot. But if I use the GUI here, so I have three options. So there's standard, and there's colored by field line length, and then there's this third one that I'll explain. So the standard plot, you can plot all of them or just pick a particular one. The standard plot will look like this, which is the points from my nimfl file, and it's also using information from my equilibrium file to get the shape of the limiter and the grid file to get the shape of the grid. If it doesn't find those files, it'll just skip over that part. And if I color by field line length, that it's really just by the number of toroidal transits before the field line exits. In this case, it's all closed flux surfaces, so it's all going to reach the maximum integration length, except for a few points out here in the open flux region. And the third option is it takes the 2D starting location of the field line and maps it to a 1D axis of the value of normalized poloidal flux and plots field line length versus normalized poloidal flux. So here's all the closed flux, and then outside the last closed flux surface, you have these short field lines. And if you have a whole bunch of nimfl files, you get a plot showing how this is changing over time. Okay, so that's nimplot, that's nimfl. Then I go back here to run because I submitted this other job, and then I just sort of left it, but it's probably long done by now since it was a very quick job, just like the other one. So it's telling me that that job is done. I'm going to fetch the results. All right, so now I have results in my tree from these two different runs. See here I have demo sim 1 and demo sim 2. So now I'm going to do is I'm going to close the main GUI, and I'm going to go to a separate section of my module called analysis. And I'm going to double click on the analysis GUI. So this is a separate GUI that is used to run analysis routines that are written in Python. So it produces this new subtree called results, and the difference between results and outputs is that outputs just contains files that were produced by NIMROD or nimplot or nimfl. Results is just going to contain arrays that are the result of processing the data in various ways using various Python scripts that are called directly in OMFIT. So the first thing, I'm going to go back to my first simulation. The first thing I can do, all this first button does is it pulls results down from the outputs tree into the results tree and just populates some 0D arrays. And once you click that button, you'll get some options here for things that you can plot. And in fact, I'm going to click that button for both of my jobs. And then the second button here will also put some 0D time traces into your results tree, but it's actually going to calculate poloidal flux quantities. So I'm going to click on that, and that's just going to call nimplot. It's going to get the poloidal flux contours for a whole bunch of time slices. And then it's going to calculate just total poloidal flux and some other quantities at each time and store that as a time-dependent array. So these are just all the poloidal flux contours that are calculated. I can just close that. But see, now I have more options of things I can plot here. And so I'm going to do this for my other run as well. But making plots here, so let's say I want to plot the thermal energy and the plasma current and the n=1 magnetic energy and the n=0 kinetic energy, say. All right, I'll close that. That one finished too. And I also want to plot total poloidal flux. Now these, I want them all on the same plot, so I'm going to normalize them all because they're probably all on different scales. And so I'm going to plot all of these for my first simulation. And I get a plot that looks like this. And then let's say I'm going to switch to my second simulation. I want to compare all those same traces on the same plot for my other simulation. So I'm going to click this again. And here's my figure. So you can see the thermal energy is dropping rapidly in that second case because I turned up K-perp. But I can just do a simple comparison of as many different quantities as I want on one plot for multiple runs. And then I can also, for instance, look at my unnormalized poloidal flux and my closed flux, or flux inside the separatrix. So that looks like that. And then I have some other analysis routines. This one calculates flux surface averages. So I could do, I tell it which dump files I want to analyze, and I say I want to calculate flux surface averages. And this is going to, again, it's going to call nimplot, it's going to get the data. It's going to average not over the equilibrium flux surfaces or the grid, but it's going to recalculate the real n=0 flux surfaces at every time slice. And it's going to do a flux surface average over those time slices at each particular time. So I'm going to close that again. So I go over to plot analysis again, and here it says flux surface average quantity to plot. So Q is one of my options. I click that button, and this is showing me the evolution of the Q profile versus time and normalized poloidal flux. I could also, for instance, plot the dBn, that's the normal component of the fluctuating fields, averaged over the flux surfaces versus time, or any number of other quantities flux surface averaged. So the temperature here is dropping, of course, in this one. Okay, and then the final analysis routine here is the poloidal FFT, giving you the poloidal mode numbers. So you pick which toroidal mode number, and you click that. And this is, again, it's going to calculate the n=0 flux surfaces at each time. It's going to figure out the straight field line angle for those flux surfaces updated at each time. And then it's going to do the poloidal FFT on the n=0 flux surfaces particular to that time slice. So I'll close that. So here I have toroidal mode. So I have two types of plots here, all M for one time slice. So I can pick, say, 0.03, and this is giving me a spectrum from -10 to 10. And this is my Q resonant line. And let's say, maybe I say, well, M=2 is an interesting mode. So all times 1M, so I'm going to say M=-2, and just see how that mode is varying over time. And this is again my Q equals 2 resonant line. So that's all of the options for analysis that are in this analysis GUI right now. I find that pretty useful. And I think that's everything that I want to demonstrate about the NIMROD module. There are other things that I haven't shown you. You can automatically initiate a scan over some parameters and get all those cases at once. Quite importantly, you can archive when you're done. I'll actually show you that right now before we finish. So I ran on NERSC. I want to just store using HTAR. So I want to archive this simulation as demo sim2.tar. This is just the full path in my archive directory. And I'll click that. And it should call HTAR, and it did not work. Okay, so we'll look into that. Okay. So sorry, my mistake was the first / there in the directory name. But anyway, so it has archived all of my dump files, which are only in the scratch directory on NERSC until I did that, and as well as all my other output files. Okay, and then so that's all. And I'm just going to save this project again, and I'm going to stop the video, and hopefully that's useful to you and you can give it a try and see if it is helpful to you. Thanks a lot.